instituições como Petrobras, CTRN, IBAMA e SEMAI de Goiás. Pesquisou muitos dos maiores rios do planeta, como Amazonas, Mississippi, Irauadi, Negro, Madeira, Juruá, Purus, Orinoco, Paraná, São Francisco, Araguaia, Ucaiali, Amarelo e outros. Coordena o Grupo Internacional de Pesquisas de Geomorphology of Tropical Rivers da Associação Internacional de Geomorfologia. Com a palavra, professora Edgardo.
Thank you very much, Tainá, for the introduction, but the start of the day is not me, but Dr. Emmanuele Gautier. It's a big pleasure having here in this seminar. I thank you, Emmanuele, for accepting our invitation. Emmanuele is an international recognized scientist, specialist in the study of fluvial systems across the world. Can you say, Tainá, she is a professor at the University Paris I, Panthéon Sorbonne, but also the director of the Laboratory of Geography, Physical Geography of the CNRS. That should be the equivalent to the CMPQ here, our CNPq. It's a big lab with that develop research across the world. Emmanuele is not a fantastic and top scientist, but is also our friend and our collaborator now in UFG, in Universidad Federal de Goiás. We're starting cooperations in the Araguaia Basin with the Labo Chef and Siam group. She's a specialist in fluvial geomorphology, hydrogeomorphology. I've been researching human impacts on fluvial systems across continents, river management, medicine techniques, and river restoration. She has a large experience researching rivers in Western Europe. For me, it was seminal her work in Bolivian Amazonia. She has been working with some of the most important meandering rivers in Western Amazonia in Bolivia. But her experience goes, what I said before, across continents. She has been working in Indonesia, for example, in Africa. And one of the most remarkable results that she has been reaching in the last decade is the study of what I consider the last frontier in fluvial science, that is the large Siberian rivers in Russia. So this is a crucial area for climate change. So she's going to talk today about the river response of the hydrological response of the system in Siberia with focus on the Lena to climate change. So I don't want to take more time. We don't have too much time. So please, Emmanuele, go ahead. Everybody's anxious to listen to you. Thank you.
Okay. Good morning, everybody, and thank you very much for inviting me. I'm very pleased to be with you. So, do you hear me? Is it okay for the language and so on?
Perfect.
Perfect. Okay. So I will share my screen and just let me know if it works. Okay for you? Can you see my screen?
Great.
Great, fine. So I will begin. Thank you very much again for your invitation. So I'm a professor in physical geography at Université Paris I, Panthéon Sorbonne. And today I will talk about impact of the current climate change on large Arctic rivers. So I will mainly focus on the Lena River, which is located in a very cold region, the Eastern Siberia. And I try to show you the response to current climate change on rivers, on those rivers draining very cold regions that are deeply affected by the current warming. So if you have difficulties to understand some words associated with Arctic regions, I will explain after. Okay, don't hesitate to ask questions. Okay, is it okay? Do you see the second slide? Okay.
Yes.
Okay, we have been working in Eastern Siberia, in central Yakutia, for the last 20 years. And we work in collaboration with the Permafrost Institute located at Yakutsk. It's a branch of the Russian Academy of Science. And you can see the team. So the Arctic regions are affected by a very important warming. In Yakutia, so it's a part of Eastern Siberia, the mean annual air temperature was minus 7.8 degrees for the last decades. It was minus 10.5 degrees before the 80s. And the most important thing is that winter temperature is subjected to a stronger increase. And nowadays, we can observe positive temperature days, even during the winter. So the mean air temperature at Yakutsk in winter was minus 35 degrees, and it's now minus 30 degrees. So it implies an increase in temperature, in air temperature during the winter of 4 degrees. That's very important. It's called the Arctic amplification. Here you can see the curve at Yakutsk, and the change during the after the 1980s is obvious. Okay, that's the last IPCC report that underlines here the observed and potential reduction in the future of the permafrost extent. And I will show how the degradation of the permafrost deeply impacts the river dynamics. So, what is a periglacial zone? The periglacial zone has several simple main features. First, permafrost. I will develop further. Second, precipitation, mainly a dry climate in continental areas, but on coastal areas we can observe more important precipitation. In the case of the Siberia, we have a very dry climate. The third feature is strong winds during winter, but also storms during the summer. And I show you that peri-Arctic and Arctic zones also include very important wetlands. First, the permafrost. Here you have the official map of the permafrost, and you can see that the permafrost represents about 23 million kilometers. In Northern Europe, I don't know if you see my mouse here, Northern Europe, and of course Alaska, Northern America, but the most important, the widest extension of permafrost can be observed in Siberia. Here you have the Russian map of permafrost, and here in Siberia, in Yakutia, you have the most important, deepest, and coldest permafrost, ice-rich permafrost here in central Yakutia, so-called the Yedoma permafrost. Because of the arid climate, only northern Siberia was covered by ice cap during the late glacial maximum. And this is the main explanation of the thick permafrost observed in central Yakutia and in eastern Siberia. And the main part of Siberia was not covered during the LGM by ice cap, so the thawing line could propagate very deeply within the soil. That explains the very deep permafrost in Siberia. I go on. So that the curve, official curve of the permafrost that have always temperature, negative temperatures. And here the permafrost is laid by an active layer that is affected by positive temperature during the summer, and that has also very negative, very low temperature during the summer. The thickness of the active layer is thinner in the south of the Arctic regions, thicker, excuse me, and much thinner in the northern regions because of the cold climate. Okay, these active layers exert a major part on several systems, on the permafrost itself, mainly because of the temperature of the active layer, but also because of its humidity content. And these active layers, I show you, also have a major part on the hydrologic dynamics. Okay, no problem with that. So some pictures of the Yedoma, the very cold and ice-rich permafrost in Yakutia. Here you can see the permafrost, all this part of the bank of the Lena River is frozen. Here you have a massive ice, pure ice, in the middle of the bank, another bank. And here you can see my colleague in the tunnel of the Permafrost Institute in Yakutsk. You can see that the mean temperature is not very cold, it's -8. Okay, within the permafrost, you can also have big ice wedges with pure ice. Okay, another picture, permafrost on the Lena terrace. And here you have a nice rich layer, pure massive ice, 20,000 years old. Okay. And now, a very important feature of periglacial zones is the richness of wetlands. As you can see here, there is a great diversity of wetlands in Arctic and peri-Arctic zones, swamps, lakes, ponds, mires, bogs, rivers, and so on. They represent a mean value of 15% and a higher value in discontinuous permafrost zones and a lower value in the continuous permafrost zones. These wetlands play an important ecological role in terms of CO2 sequestration and mineralization, but I'm not going to develop this point. Here, that's an image, a satellite image of Yakutia. You have the Vilyu River here, a main tributary of the Lena River, and you can see numerous lakes, and these lakes are called thermokarstic depressions because these lakes are installed on the permafrost. Okay, that's a schematic profile. You have lakes, ponds, mires, and all the diversity of wetlands located within the permafrost. Here you have the active layer, and I represent also ice wedges. And under lakes, thermokarst lakes, you have the thallic, that's a non-frozen part within the permafrost. Here you have the active layer, and these active layers is a small perch aquifer, and that's the main source of water on plateaus. And these explain the impermeability of the permafrost, explain the presence of numerous wetlands. Okay, I go on. Some view of different wetlands, and here you have the Lena River. So there is a paradox between the very dry climate and the richness of wetlands. In Siberia, there are two main biomes, tundra and taiga, and these main biomes are limited by two main parameters, the number of days without negative temperature and the mean temperature of the warmest months, usually July. Okay, and taiga is the widest biome on Earth. I show you some pictures of the taiga dominated by Picea, mainly by Picea obovata, and near the wetlands you have other species associated with the humidity of the soil. So we have a very cold region and very humid region. Here that's the view of the weather forecast of Siberia, and you can see during the winter the weather can be awfully cold. And if in French we used to say it's a duck cold. It's very cold, it's French expression. So now, what's the impact of warming on hydrosystem? As I said before, an important warming is observed from the 1990s. Here we can see the yellow curve expressing the very important warming of the region. So what are the impacts on Arctic rivers? And I will show you that response of Arctic rivers is quite complex. Concerning the precipitation, we can't see a very clear trend. Here you have mean annual precipitation since 1936, I think, and you can see a very clear trend. There are very dry periods and much humider period. During the period 2002 and 2008, very important precipitation during the summer were measured. So, to evaluate the impact of the global warming on Arctic region hydrology, we have to distinguish the effect during the summer and during the winter. In the winter, the strong increase in air temperature limits the freezing wave propagation into the soil. So that's the main factor explaining the increase in the thickness of the active layer. The summer can also have a major impact when the summer is very humid with a lot of precipitation. And as I just said before, it was the case between 2002 and 2008. The two evolutions, summer and winter, provoked the degradation of the permafrost. Here you have the view of a part of eastern Siberia, which is affected by a strong degradation of the permafrost. And you can see the former level of the soil. And here, because of the sowing, it's not very correct to say sowing for the permafrost, but because of the degradation of the ice wedges, you can observe the soil collapse. And here, a new lake formed by the stronger humidity of the active layer. The main impact of the warming is the increase in water connectivity between plateaus and rivers. This increased water connectivity is created by the increase in soil humidity, soil moisture in the active layer. So we have a deepening of the active layer and an increase in the soil moisture. This induces a stronger connectivity, water hydrologic connectivity between the plateaus and the river. Here you can see on this picture, for example, the ice wedge network, the former ice wedge network that is completely degraded and now occupied by water. So all rivers in discontinuous and continuous permafrost regions are undergoing a positive strain of their water discharge. And in some cases, in numerous cases, we can also observe a strong increase in flood magnitude and flood frequency. I will develop now this point. First, to illustrate the stronger humidity on plateaus, I show you the work, the research conducted for many years by our colleagues from the Permafrost Institute. And here you have pictures of thermokarstic lakes at different dates. And you can see the widening and the deepening of these thermokarst depressions. During the very wet period, 2002-2008, our colleague evidenced a strong deepening of the thermokarstic lakes because of the permafrost degradation, and this was associated with very humid summers. The degradation of permafrost also provokes the destabilization of the banks, mainly in this case, the banks of the lakes. Here you can see the so-called retrogressive thaw slumps on a lake bank. You can see the ice wedges, and because of the warming and the soil moisture, our colleague observe large mud flows provoking the degradation of the bank. The same observation can be done on rivers, but I will explain it precisely. The destabilization of lakes, the extension, the widening, deepening of lakes have very important impacts of local populations. And they also disrupt wetlands, hydrochemistry, and sedimentation. So now, as you can see, there is a higher humidity on plateaus, and these induce an increase in water discharge of rivers. Another picture of the Central Yakutia. A recent publication of our colleagues demonstrated that a strong increase in water supplied by lakes. It was about 5% before 2004, and now the water supplied by lakes to rivers represent 1/3. Here you have a table of the main Arctic rivers located in Alaska, northern Canada, and the four largest are located in Siberia, with from west to east Ob River, Yenisei River, Lena River. And to the very east, far east, we have the Kolyma River, which is smaller, but even a large river. And you can see that the majority of these rivers have the main part, the 2/3 and more of their basin covered by continuous permafrost. Here is the map of the Arctic River. First, I show you studies for rivers located in Northern Europe, and after that, we developed the impacts of global warming on the Lena River. On this picture, on this figure, you can see that these rivers are characterized by a very irregular discharge, water discharge. They show a very low discharge in the summer, in the winter, and a very strong discharge, very high discharge at the beginning of the spring, generally in May or June, depending on the location of the river. For example, on the Yenisei River, you can see that the main monthly discharge in winter is only 6,000 cubic meters per second, whereas it is more than 80,000 cubic meters during May. The same observation can be done for the Lena River. The Mackenzie River has a lower irregularity because the Mackenzie Basin has a lot of lakes. Now, the example of the response, hydrologic response of rivers located in Norway, in northern Norway. Here you have the Google map, Google Earth image of the regions. And the research is conducted by Westermann, Etzel Müller, demonstrated that all the rivers in Norway, Finland, and so on, are undergoing a strong increase in water discharge. Here you can see the main conclusion of their papers. The average discharge in the winter months, November to February, and the annual minimum discharge have more than doubled. That's a very impressive evolution in terms of rapidity and intensity. In Northern Europe, the hydrologic response of the river depends on the part played by the permafrost extent and the snow cover and the part played by summer precipitation. So to summarize, there is on all these Northern Europe rivers an increasing trend in stream flow frequency. They also observe earlier fluvial outbursts and flood peaks, in spring. And they also measured increasing frequency in rainfall in winter, and an increasing part of rainfall-dominated floods versus snow melt-dominated floods. It means that precipitation, rainfall, nowadays plays a more important part than before because of the reduction of the snow during the winter. I hope I'm clear. If not, you will ask questions. Now, what is the situation concerning the rivers that have a very important part of their basin covered by permafrost and continuous permafrost? And for that purpose, I will develop the case of the Lena River in eastern Siberia. Here is the section of the river have been studied for many years in central Yakutia. And we are in a very cold area, the coldest region of the northern hemisphere. And you can see that 77% of the catchment is covered by a continuous permafrost, and I show you pictures before. The Lena River has a very low water discharge during the summer, like other Arctic rivers, and a rapid increase. You can see the curve at the end of the winter. There is a 0-1 evolution, no water, and in few days, a very important discharge. And you can see here in May, the peak discharge and a rapid falling limb during the summer. And here, a new peak at the end of the summer. That's a new feature, a recent feature of the Lena River. The red curve shows you the last decade mean monthly discharge of the Lena River just upstream of Yakutsk in a pristine region affected by no dams. Okay. So you can see that the red curve evidences a strong increase in water discharge for every month and a new flood peak at the end of the summer, as I said before. During the winter, the Lena River has a low water discharge, lower than 1,000 cubic meters per second, and the Lena is covered, as you can see on the picture, by a thick, approximately 1 meter thick ice cap during more than 200 days per year. At the end of the winter, a flood wave is coming from the southern part of the basin. These flood wave forms at the end of April in Prebaikal region, where the climate is less cold. Okay, and these create a flood waves that will propagate downstream, and this flood wave will reach the region of Yakutsk 1 month later, and it still needs 20 days to reach the Lena Delta. Here you have a picture of the very beginning of the fluvial outburst. The fluvial outburst is the very beginning of the flood. You must imagine that the flood wave coming from the south will lift up the ice cap on the river, and the water level will increase very rapidly. The water level can rise up to 8-10 meters in only one day. Here you have the example of the flood of 2010 in May, and you can see a picture taken in May 18th and the day after, and the water level rise up by 10 meters. And very big ice jams were formed on the head of the main islands of the Lena, at the entrance of the secondary channels. In 2010, it was an historical flood. It was the second one since we have hydrologic data on the Lena River. First, you have the outburst. It means the breakup, the destruction of the ice present on the river. And the second part of the flood is a huge inundation, as you can see here, on the floodplain. Here in central Yakutia, the width of the floodplain ranges between 10 and 20 kilometers. So it's a big floodplain. That's a normal life of the Lena River. So, how the global warming modify the hydrology and morphodynamics of the river. The first impact concerns the water temperature that is strongly increasing. We have demonstrated that more than 10 years ago that the water stream temperature is deeply impacted by the warming. As you can see here on the curves of the water stream temperature in May, June, and July during the flood season, you can see that more than 10 years ago, we already observed an increase of more than 1 degrees, for example, in June. So that's an important increase that reflects the air temperature change. So the water is warmer. Thus, we measure the water temperature during the summer, and I show you the water temperature from May to June. But the water temperature is also warmer during the winter. That's why the ice cap thickness is reducing. And now the ice cap during the winter is much thinner than previously. And this represents an important risk for local population because Yakutian used to drive on the ice cap during the winter with cars and trucks, and it's much easier to drive on the frozen Lena than to drive on the roads. And nowadays, many accidents are observed because the ice cap is much thinner. An important change is also observed concerning the water discharge. The mean annual discharge has increased by a mean value of 12%. But since 2006, the increase reached 30%. That's an unknown evolution in terms of intensity and rapidity. This increase in water discharge is recorded in winter, in early summer, but also in late summer and early autumn. And I already underlined the increase in September, August, September in the water discharge. For the last 2 decades, all mean annual discharge were characterized by positive anomalies, except 2 years. So we have a very important water increase on the Lena River. The frequency and intensity of floods is also changing. And for an example, here you have the last decade, and you can see the very important change of flood temporal distribution. Now we can have much earlier floods, but we can also have very late floods occurring in August or even in September. And then that's an unprecedented situation. The duration of floods is also increasing, and several years underwent a very long duration of inundation in the floodplains, creating numerous problems to the local population. Here, that's a graphic for the date of the beginning of the flood in May, and you can see that since the beginning of the 21st century, the flood can begin much earlier, up to 10 days earlier. So, how does the river react in terms of fluvial geomorphology, erosion, and sedimentation? You have to remember that the banks of the Lena River are formed within the permafrost. Here you have a picture of a bank of a terrace with Picea obovata on the top. The permafrost, here you can see it with thin, massive ice layers. And here you have large slumps, in Russian Bajrak, because of the thawing, the penetration of the warm heat propagation within the banks, which creates slumps. Okay. And many years ago, we shown that islands banks, the banks of the islands, are much more sensitive to the process of bank erosion because of fluvial dynamics, fluvial currents during the flood, but also because of so-called thermal erosion. The thermal erosion means the heat exchange between the water, the warm, not very warm, but warm water during spring and summer, and the frozen bank. Okay? And we show that the island banks are very sensitive to the thermal and mechanical erosion. So, on the basis of satellite images and also pictures, corona pictures, we have conducted 50-year survey of more than 100 islands in order to determine the potential change in terms of erosion and sedimentation of islands. Okay, so we precisely determined the part of the island that is eroded and sedimented, and the pattern of evolution of islands, if they are merging or separating, and so on. Okay. We also work in the fields during several years on occupied islands, 5 occupied islands, but we lost one because of a total erosion during the 2010 high flood. Okay, so we measure erosion sedimentation. We had also sensors to measure temperature of water, soil at different depths, permafrost, of course, and so on. Okay, we measure erosion, sedimentation, we realize permafrost drillings, and so on. Okay. On the basis of our GIS, we identified several changes. The main change is the multiplication of very small islands in the fluvial bed. Here you have the number of islands for the study area since 1967 and till 2017. And you can see that at the beginning of the period, we had less of 100 islands, and now we have much more. So the part occupied by the fluvial bed by islands has increased, and the number of islands has increased. However, the evolution is relatively complex because we have a multiplication of very small islands. Now you can see the small points, blue points, that depends on the size of the new islands, whereas at the beginning of the study period, we had new islands that were much larger. Okay? This is related to the decrease of the deposition in the fluvial bed. Okay? And that explains why here you have the distribution of the surface area of island, a decrease since the beginning of the century of the island size. Okay? Now, to understand the evolution, the complex evolution of the river, we connect erosion and sedimentation values with the main hydrologic features. And here you have the 4 occupied islands. I explained we have lost one in the fluvial bed. And we measure precisely erosion and sedimentation of these islands. Okay, these are the main values for the 4 main study period. Okay, and we identify 2 main factors explaining the strongest erosion of islands. Here you have islands banks after the flood, and you can see the strong erosion of these islands. The main parameter controlling the erosion is not the flood peak, the flood intensity, but it is the flood duration. The longer duration, the stronger erosion. The second factor explaining the increasing erosion of islands is the occurrence of late peak, a late flood peak, occurring in the late summer, mainly in August or beginning of September. And these late flood peaks are characterized by a warmer flood stream temperature. And the combination between longer flood duration and warmer floods temperature explain the increasing erosion and the destabilization of the fluvial bed. Here you have two islands head here, and the evaluation of erosion for every year. And for example, in 2009, we had a long duration of submersion on the islands and floodplain, depending on the island level, elevation. The inundation ranged between 20 and 30 days. And during this year, 2009, we measure a very strong erosion of islands. Here you have the pictures. We also observe thick deposits on the island tail, downstream part. In 2012, an opposite example, different example. During 2012, we had numerous secondary flood peaks. Here you can see 4 peaks, 4 flood peaks. And here, I hope you can see it, it's the stream water temperature we measured. Okay, and here you have the temperature in May at the beginning of the flood, and here at the end of July. Okay, and you can see that at the beginning of the flood, the water temperature is not very warm. It's about 1-2 degrees Celsius. And at the end of the summer, in July, August, the water stream temperature is much higher, reaching 20 degrees. So it's pleasant to bath in the Lena River. Okay? But these very warm temperatures induce a strong thermal erosion of the frozen bank. And these explain the destabilization of the fluvial bed, mainly through the islands. Okay, so we identified 2 types of islands concerning the permafrost. To be formed, a permafrost needs at least 30 years within islands. We determined by drilling and by temperature measurements that only old islands exceeding 30 years old have a permafrost. Younger islands don't have a permafrost. They are frozen during the winter, but unfrozen during the summer. And therefore, the permafrost needs at least 30 years to be present. Okay? And when I examined very precisely the different generation of islands, I discovered that before the end of the 20th century, the island without permafrost eroded more rapidly. And nowadays, since the beginning of the 21st century, the frozen, I mean the islands with a permanent permafrost, erode more rapidly than non-frozen islands. And it's an important result because numerous islands in the fluvial bed of the Lena River are old islands. And this explains why the fluvial bed is presently affected by very rapid changes in terms of sedimentation and erosion.
Emmanuele,
yes?
Sorry for interrupting you. The translation system is time sensitive. It's finishing 9:45 talk.
Okay. So I have
Sorry
finished.
for that.
Yes, excuse me. Okay, so it's my conclusion. These evolution have strong impacts on local population, on navigation, on fluid risk, and so on. So, excuse me for being too long, and thank you very much for your attention. If you have questions.
Well, thank you. Absolutely. Thank you very much for the great talk. We have probably time for one or two questions. You can probably, sorry for interrupting, just try to inform you. You can run the last ones you want. We have a couple of questions. One is about the impacts on the human population. You mentioned something about that, how the society is reacting at this point in the area.
Would you like me to answer immediately?
Yes, please.
Yeah, okay. The instabilities, increasing instability of the fluvial bed is a huge problem for the navigation. The Lena River is the main economic link for the local population. It's the main way for exportation of gas, wood, and all goods from the Lena Basin to the Laptev Seas and to the northern regions of Europe. So the destabilization of the fluvial bed is a major economic problem. And the second problem is the increasing frequency and duration, the increasing duration of the floods. But in Russia, the protection of population against floods is not very developed. So except the solidarity, the local solidarity, nothing is done.
Well, other questions are related more or less to the same, on how the melting of the permafrost also affect the infrastructure of the local region. And this can impact the movement of people to different kind of activities when the permafrost melts. This can impact as well.
Excuse me, I don't hear you very well, Edgardo.
Yeah, people is asking more about the collapse of the sowing of the permafrost. This impact the city's infrastructure or the economic activities. A little more of the one that you have been explaining.
You mean the collapse of the banks?
Yes, and the thawing of the permafrost.
Yes, the thawing of the permafrost creates numerous problems to cities because of the collapse, the inequalities created by on the soil because of the permafrost degradation. It creates numerous problems, houses collapse, problems to canalizations of gas, water, and so on. And there is another impact. The ice formed on the river during the winter is an important water resource. The local population used to cut the ice to have good quality water, and they will make some cubes and put them in their cellars in the permafrost to have drinkable water during the summer.
Thank you very much. I think we are going to close the presentation because it's finishing our translations service. Yes.
Sorry.
Please go
You
ahead.
can finish. Dr. Gautier, Professor Edgardo, on behalf of the organizing committee, I would like to thank you for your participation. Thank you very much, Doctor.
Thank you very much.
Great talk. Yeah. Great, amazing talk.
Okay, thank you very much for your attention.
Thank you.
Bye-bye, and see you soon.
Obrigada a todos vocês que nos acompanharam nessa manhã. Lembrando que para receber o seu certificado de participação, você tem que assinar a lista de presença que está fixada no chat. Os books e cadernos de resumos do evento, eles serão disponibilizados, os e-books, assim que forem liberados pela gráfica, mas você já pode ter acesso aos anais do evento com os resumos de todos os trabalhos que foram aprovados no site do LaboGef. Eu convido vocês também a assistirem os filmes e documentários que foram disponibilizados pela parceria com a Ecofalantes Universidades. As instruções elas foram encaminhadas por e-mail aos inscritos do evento, mas caso vocês não tenham recebido, é só entrar em contato com a equipe da organização. Eu peço também que todos vocês continuem conosco na nossa próxima atividade, que ocorrerá às 10 horas da manhã, com a mesa temática Bacias Urbanas Sustentáveis. Até breve.